Good afternoon, everyone. Thank you for being here today. My name is Sudarshan Kasera, and I'm a structural engineer with over 10 years of experience in the telecommunications tower industry. Today, I want to share how we can leverage data analytics to fundamentally improve the way we approach structural analysis of telecom towers. This presentation will cover the structural engineering fundamentals that underpin tower analysis and design, and then show you where data driven methods can add tremendous value to this traditionally manual process. Whether you are from the tech side or the infrastructure side, my goal is to somewhat bridge these two worlds and show the opportunity ahead of us. Load demands on towers is increasing due to network upgrade requirements such as 5G. Equipment is getting larger and heavier, while the overall infrastructure is aging. Many towers in the US were originally designed in the 1980s and 90s for much lighter antenna loads. The average structural load on existing towers has grown significantly with each generation of wireless technology, from 2G to 5G. The tower infrastructure market continues to expand through 2030, driven by densification and rural broadband initiatives. Continuous uptime is no longer a luxury, it is a critical requirement. Tower supports public safety communications, emergency services, and essential connectivity. It becomes critical that structural analysis accurately captures all tower components to maintain continuous network uptime. This is where data analytics can play a transformative role. Before we talk about analytics, it is important to understand the engineering standards foundation that governs everything we do in tower structural analysis. International Building Code, or IBC, is the overarching legal code adopted by most jurisdictions in the United States. It serves as the umbrella under which all other standards operate. NCTIA 222 is the primary standard specifically developed for antenna supporting structures. It covers towers types including self-support towers, monopole, guide towers, and any other infrastructure supporting wireless equipments. The current revision of the code is Revision I. ASCE 7 provides the foundational environmental loads, including wind speed maps, ice loading criteria, seismic parameters, and their load combination. TIA 222 references ASCE 7 and adapts its provisions for tower-specific applications. AISC 360 governs the design of structural steel members and connections. Since the vast majority of telecom towers are steel structures, this standard is critical for member capacity checks. ACI 318 covers reinforced concrete design and is essential for tower foundation design, including drill shafts, split footings, and mat foundations. These standards form an integrated framework when we talk about automating or applying analytics to structural analysis. We must ensure full compliance with this code hierarchy. This slide covers the critical load types that every tower must be designed to resist. Understanding these loads is essential because they are the core inputs to any structural model, whether traditional or data driven. Dead loads include the self weight of the tower steel, platforms, ladders, antenna mounts, and all mounted equipment such as antennas, radios, junction boxes, and feed lines. Accurate dead load accounting is fundamental and is an area where data analytics can significantly reduce errors in equipment inventory. Wind loads are typically the governing load for most telecom towers. We calculate velocity pressure based on the basic wind speed from ASCE 7 wind maps adjusted for exposure category, topographic effects, and height above ground. The wind loads and antennas and appurtenances can exceed the wind load on the tower structure itself. Ice load is critical in certain climates. TIA 222 specifies radial ice thicknesses maps, and towers must be analyzed for ice weight plus concurrent reduced wind loads. Ice can dramatically increase the effective projected area of members and antenna. Seismic loads are evaluated based on site classification, mapped spectral acceleration, and the response modification factors for the tower type. While wind typically governs tower design, seismic loads can control foundation design in high seismic zones. Thermal effects, while sometimes overlooked, can introduce significant stresses in constrained members, especially in guide towers and long monopole sections with large temperature differentials. The key point for this audience is that each of these load types generate large volume of site-specific data. Structuring and analyzing this data at scale is where machine learning and analytics begins to add value. Modern structural analysis software such as STAD, RISA Tower, and TNX has significantly advanced our ability to perform detailed finite element analysis on tower structures. These platforms automate the application of hundreds of node combinations required by TIA 222 and ASCE 7 and perform by member design checks against AISC 360 capacity equation. This alone has dramatically reduced analysis turnaround time compared to hand calculations. Documentation and reporting is arguably the most important deliverable in any structural engineering project. The structural analysis report, along with sealed drawings, is what gets submitted to the local jurisdiction for a building permit. Without a permit, no construction or modification can proceed at the site. Standardized reporting formats that meet regulatory requirements are essential to obtaining permits efficiently. Tower operators in the US own anywhere from hundreds to over 40,000 towers. For operators at that scale, centralized data integration is critical. Accurate and clean data can reduce the time spent on each tower analysis cycle and also accelerate troubleshooting for maintenance-related structural issues. This is where we start to see the convergence of traditional engineering softwares with data platforms. When analysis results are stored in structural databases rather than isolated PDF reports, we unlock the ability to perform portfolio-wide trend analysis and predictive insights. High-quality data is the foundation of any analytics or machine learning initiative. In structural engineering for telecom towers, the key data inputs come from multiple sources that must be integrated. Structural data sets include material properties such as steel grade, yield strength, member dimensions, including leg sizes, bracing patterns, bolt sizes, connection details, foundation specifications, etc. These are the building blocks of any structural model. Stress ratios or demand to capacity ratios are the primary output of structural analysis. Tracking stress ratios across all members and across multiple analysis runs provide a rich data set for identifying trends. Similarly, deflection data can include historical displacement measurements, serviceability limit checks, and dynamic response characteristics such as natural frequency and vortex setting susceptibility. Inspection records capture field conditions that model alone cannot predict: corrosion progression, connection loosening, foundation cracking, and any member damage. When digitized and standardized, inspection data can become a powerful input for predictive maintenance models. Key message here is that each of these data streams independently has value, but when combined and structured, they enable a level of insight that was previously impossible in our industry. This slide illustrates the evaluation from traditional structural analysis to where we want to go, that is, intelligence-driven infrastructure management. Think of it as a maturity curve. On the left, we start with traditional structural analysis. This is the code-based, standard-driven approach that has been the backbone of the industry for decades. It works well, but is inherently reactive and project-specific. The next step is digital modeling, where we move from 2D drawings and static reports to full 3D finite element models that can be updated and reanalyzed as conditions change. This is where I feel we are at today. Data integration is the critical middle step. This is where we connect analysis results, inspection records, environmental data, and equipment inventories into a unified data platform. Without this step, analytics, and machine learning have nothing to work with. Analytics then allows us to query these integrated data for trends. Which towers in our portfolio have the highest stress ratios? Which regions show accelerated corrosion? Finally, predictive analysis. This is where we want to be. Predictive analysis can use machine learning to move from descriptive insights to forward looking predictions. Instead of asking what happened, we can ask what is likely to happen and when. Each stage builds on the one before it. You cannot skip straight to machine learning without first having structured, high quality engineering data. This is a message I want to emphasize to the tech community. The engineering fundamentals must come first. Let us talk about the tangible business impact of adopting a data centric approach to structural engineering. The extended surface life is perhaps the most significant benefit. Proactive monitoring and data driven maintenance decisions can extend a tower's operational life well beyond its original 25 to 30-year design expectation. Given that a new tower build can cost several $100,000, extending the life of existing assets by even 5 to 10 years represent enormous capital savings. Reduced liability is critical in our industry. Comprehensive documentations and consistent analysis protocols provide strong defensibility in regulatory audits and legal contexts. When every analysis decision is traceable and every inspection finding recorded in a structured database, the operator's risk exposure is significantly reduced. Proactive decision making is enabled when analytics ready reporting reaches leadership teams. Instead of reactive capital expenditure driven by emergencies or permit deadlines, executives can make informed capital allocation and risk management decisions based on portfolio wide data. These business outcomes represent real revenue and cost optimization opportunities. To wrap up, the future of resilient telecommunications infrastructure lies at a convergence of four key elements. Traditional engineering provides the standards based analysis and proven design methodologies that ensure safety and code compliance. This foundation is non negotiable and must remain at the core of everything we do. Structured data transforms isolated analysis reports and inspection findings into queryable, analyzable datasets. This is the enabler that bridges traditional engineering with modern technology. Machine learning takes structured data and builds predictive models and intelligent monitoring systems that can identify patterns human would miss across thousands of towers and millions of data points. The end result is resilient networks, safer infrastructure that supports the critical communications our society depends on, managed more efficiently and with greater confidence than ever before. One message I want to emphasize in all this: the engineering fundamentals must come first. Thank you for your time today. And below is my email address and LinkedIn URL. If you want to reach me anytime, please feel free to do that. Again, thank you for your time today. I greatly appreciate it. Thank you.